Okay, example 5. A heavy rope 50 feet long weighs half a pound per foot and hangs over the edge of a building, 120 feet high. How much work is done in pulling the rope to the top of the building? Let me just mention one thing real quick. As of right now, the height of the building does not matter as long as it's longer than the rope. And it will be. If the building was shorter than the rope, that means you have a pile of rope on the ground, right? So as you pull it up for a while, the same weight's going to happen for a while until you eventually get the rope off the ground. Then the rope's decreasing in weight from that point forward. All right? But for right now, the rope's going to be longer than the building. That's the reason the height of the building is 120. It could have been 51 feet high, 5,000 feet high. The answer is going to be the same for this problem. If the building was 30 feet high, the answer would change. All right, because then the rope's sitting in a pile, so you got 30 feet of rope going for a while until you get 30 feet of rope there, then the rope changes weight from that point forward. It becomes a little bit more difficult, but not much more difficult to do that. So, heavy rope, 50 feet long, weighs half pound per foot. Let me just mention this. This is the unit you want when the weight of anything is changing. Pounds per foot is going to be helpful. Okay, and in one of your homework problems, you're not going to get that specific unit, but you can create it with the stuff they give you. So if you don't have a pounds per foot, use the information they give you to create a pounds per foot. Use basic algebraic structure of fractions and put things in the right places to cancel things out to create that unit on your stuff. Now, what's happening here is this. We have a building, we have a rope, let's just say it's like right here. They like tapped a nail into the top of the building there to put the rope in place and it hangs over here. The rope is 50 feet long. The initial position of the rope, let's say this is 0 and down here is 50. We're going in the opposite direction here. All right? The point on the rope I care about is this point right here. That point, the end of the rope. All right? That's what's changing position. This is what's going to give me my interval for the integral I'm going to create. I'm starting at a position of 50, I'm ending at a position of 0. Okay? If I wanted to pull the rope up only 10 feet, 50, 40. All right, so my integral will go 40 bottom, 50 top. All right? This is going to be 0 bottom, 50 top. But just know that if I move it 10 feet, it's not 0 to 10. It's 40 to 50. Because the weight of the rope is going to be heavier down there than it is up here. So keep that in mind when you're creating these integrals. When the weight of the rope matters, then that's going to affect our weight. Okay? The only thing that weighs anything in this problem is the rope, right? There's nothing attached to the end of the rope. All right. So the weight of the rope is equal to half a pound per foot times the number of feet. Okay? Now obviously it's a 50-foot rope, right? So when I multiply this times 50 feet, that's just how much the rope weighs. All right? But once I pull a foot of the rope up, now there's only 49 feet of rope. Once I pull another foot up, now there's only 48 feet of rope. So the weight's changing. As we're pulling it up, there's less rope hanging, because as we pull it up, the rope's just sitting in a pile on the top of the building, right? So the rope's getting shorter, shorter, shorter as we pull it up, so the rope's changing. So instead of getting a weight as an exact number here, we're going to do weight equals half a pound per foot times X feet of rope that's hanging down at any given point in this problem. X feet times half a pound per foot, foot cancels foot, that gives me a weight of the rope at any given point in this problem is going to be 0.5 X pounds. This is known as variable weight. Okay? If the weight changes, it's variable, so you need a variable to represent the weight. Okay? If something in a problem doesn't change weight, it just is a number. For example, in the problem number 14, you're going to get, you have a 4-pound bucket. The bucket's going to be 4 pounds the entire problem. Okay? It's not going on a diet halfway through. It's going to stay 4 pounds. There's going to be water in the bucket. That water weighs something also. That's going to be exactly what the water is every time. The water's leaking out of the bucket. That's changing the weight, so you're going to subtract the weight of the water that's being taken out as the bucket gets raised. All right? So that 4 stays the same, 40 stays the same, but minus some variable weight of water that's dripping off. Okay, so you could get constant values within the weight, but you could also get variable values within the weight. So the weight of this rope is half a pound X for wherever it's at. All right? So that's what I want to integrate. Oops, dx. As with the problems we saw yesterday, pounds is force, and we want to integrate force in order to get work. All right? So my force function on this one is just that. If there was some kind of a, let's say there's a 20-pound weight on the end of this, now the weight function is going to be 0.5x plus 20 pounds. Because for the entire time the rope's being pulled up, there's a 20-pound weight on it, right? It stays 20 pounds all the way through. So again, you can get constant weights on there also, along with variable weights. There isn't a 20-pound weight on this one, so we'll erase that and erase this. All right. Now, the other thing again is where we're going from and to, so we're looking for work. Force goes here, pounds goes here, distance goes here, and again, my initial position is 50, my final position is 0, so 0 to 50, right? Final to initial, that's where you want to put these, all right? And again, the fact that the building's 120 feet high just means that's a free hanging rope. There's not a pile of rope on the bottom that's going to weigh nothing as we're pulling it up. Okay, so that's the integral, and now we simply have to work it out. 0.5x is going to be 0.5x squared over 2. We're going from 0 up to 50. I could make that 0.25x squared if I felt like it, but my calculator's evaluating stuff, so I'm just going to type it in. So 0.5 times 50 squared divided by 2 equals 625. Now notice, this is pounds and feet, right? So we're dealing with pounds and feet, so it's going to be foot-pounds for a unit